Hello everyone. Today I just want to go through one of the more interesting topics in horizontal circular motion, and that is banked tracks. Now before I get into it, I'm just going to cover the quick basics of circular motion. So let me attempt to draw a circle here. So here's a circle, and let's say there's an object. I'll put it in blue. Just give me a moment. Let's say there is some object attempting to stay on this righteous circular path. So it's traveling in this circular motion, and we'll say that the radius of this circle, or more like a funny looking potato, but imagine it's a circle, is some radius r. Now we know that this object's velocity is tangential to the curve. It wants to go this way, but it will maintain a perfectly circular path if it has a centripetal force acting inwards to the center of that circle. So if this is the case, then this object will maintain a circular path, and we've seen it for some cases. Let's say you had a let me get a different color. Let's say you had a rope here, and you attached that rope to a bucket of some sort with water in it. Let's say, I don't know, whatever. And this was getting swung around in your head, and it went around in a perfectly circular path. That centripetal force keeping it in that circular path is the tension in that rope. Or in another example, if you had two planets, say, or the Earth and the Sun, or whatever kind of gravitational planetary system you like, they are attracted to each other due to a force due to gravity. And if the situation is just correct, they will orbit, or one body will orbit the other in circular motion, because the centripetal force is the force due to gravity in this case. So we've been talking a lot about horizontal circular motion and where the centripetal force actually comes from. And we know it always acts to the center of the circular motion, And we also saw, in a previous class, that the formula for centripetal force was that the mass of the object that's in the path multiplied by its velocity squared divided by r. Okay, that is the formula for centripetal force, and we're going to talk about that a bit more later on in some more interesting scenarios. But I want to throw you into a scenario where it's not quite evident where the centripetal force is coming from. So, for instance, let's say we had a car and we wanted to allow it to turn a corner. Now there are two things typically that can happen when a car turns a corner. Either this or this. Okay? In the left example, with this white car, somebody is trying to turn into their driveway, and the unlucky driver happens to not being able to make the turn, and they just end up sliding down the road. In the right example here, with this nice looking orange car, the driver is able to make the turn quite well. The question is, why? They are both trying to enact some form of circular motion, but why is it that the left driver is having a bad day and the right driver is doing just fine? What is the actual difference here? And you may be able to immediately tell it's got something to do with the surfaces here. You can tell in this example here, it seems like quite a cold night, and it seems like the road is quite icy, and so the wheels aren't able to grip on the road and actually allow it to go in circular motion. As opposed to the right, where the wheels can grip quite well. And you would be correct in saying that the grip has something to do with it, but how much to do with it is the question. So let's have a closer look. So let's say this is our car, and let's say we're the orange car. We don't want to go down the street, and we're turning the corner. Now the car wants to travel in this direction. Okay, that's its velocity. It wants to travel to the left. But we know that in order to allow it to travel in a circular path, it must have a centripetal force acting towards the center of that circle. Okay, so it must have a centripetal force, and that allows it to maintain this to change its velocity in the direction of this blue arrow here. Okay, this is its new velocity. You could say that. Okay. Now, according to Newton's first law, the car really does want to stay on this leftward path. It wants to veer out and maintain this path and keep going off here. But some centripetal force is keeping it towards the center. Now the question is, where is this centripetal force actually coming from? We know it's there, but where does it actually originate from? And therein lies the question. And I'll just flick back for a second. The drawings are going to stay. Remember, the grip in the road had something to do with it. And so a particular word might pop into your head, and that is friction. Happens to be helping us out here. Now we typically think of friction as this annoying kind of resistive force that opposes the direction of a motion, and it does for quite a few cases. But in some cases, it can actually help us enact motion. And in this case, it does. Whilst the car wants to travel out towards the left, friction is actually keeping the wheels from veering off in this kind of direction here. And so there is a frictional force that's acting against that motion, against this velocity here, and allowing it to keep the car in this circular path. So this centripetal force is actually due to the frictional force of the wheels with the road. Okay. So in this case here, friction is working to our benefit. In this case. Okay, if this was an icy road, it would not go so well. Now there's a kind of interesting caveat, or interesting consequence I should say, that comes across this. If the car is going really fast, then you're going to need a higher force due to friction to maintain the centripetal force, and that comes directly from this equation here. Right? If your velocity is higher, then you're going to need a greater centripetal force, and that means you need a greater force due to friction to keep this car on the road. And so you're going to need better tires, or better threads, or a better type of surface of the road. But it's hard to just change your tires or change the surface of the road. So if the frictional forces of the tires weren't good enough, and you're traveling at a significant velocity, then your car is going to skid off, and it's just going to go off the actual circular path. Okay, so when it comes to cars turning corners, it is a balance between the friction of the tires on the road and the velocity of the car itself, and the tightness of the actual turn itself, the radius of that circle. Okay, and that's primarily why you might see signs on the road, right, 50 k's an hour, and there's a curvy road here. Why there's a speed limit with tight turns to suggest to the driver to slow down so they can reduce the amount of centripetal force necessary, and hence the car will have the frictional force capable of performing that turn effectively. The question is now, what if we didn't have friction to help us? What else could we use to allow an object to make a turn? Or a different kind of question could be, what else could we add to this kind of to an object that's turning to allow it to turn more effectively? Okay, and I'm going to show you some examples, and you're going to be able to pick out the common thread very clearly here. So here's the first example. Here's a velodrome with some cyclists all down the bottom, and you notice they're racing around this track. The track doesn't look normal, in quotation marks. There's something interesting about it. You can kind of see it here. You can definitely see it here. You can see it by the way these cyclists are leaning. Okay, there's something interesting going on the track here. You can see it very directly in some car races, especially NASCAR. There's something interesting going on with this track here. And very, very clearly this track is sloping somewhat. Okay, you can get some extreme examples where some daring motorists can actually ride on a near vertical wall here, but they need a sufficient velocity to do so. And you can see it almost looks like they're hovering in midair. Okay, but they just manage to maintain this circular motion with this kind of interesting road that's tilted, so to speak. You can also see it in some trains. Here's a little gif of a train. It's tilting as it turns the corner there. Okay, and the question is why is it beneficial to do this? Well, first of all, each of these examples is an example of a banked track. Okay, so I just want to go through the physics of banked tracks and how they differ to some other physics that we've covered previously. So let me draw one up for you, and you can see this drawing in quite a few places. Eddie Wu has a fantastic series of videos on it, and I'm gonna take a bit of inspiration from it. So here, imagine here you have a road. Now this is a banked road. It is at a certain angle. Yeah, it is at a certain angle. The road itself is tilted. Okay, the road itself is tilted. And let's say we had some object, a cyclist, a car. Let's just say let's just call it a car. There's a car on the road. I'm going to represent it by this dot here. And it wants to travel along this path here. Okay? Let's travel along this path here. Now this curve has some radius r. Okay, some radius r. Some angle theta. It might have some height h. Okay, and then it might have a certain width as well. Well, it has to have a certain width. Okay, d or w, whatever you want to mention it. We're gonna ignore d and h for a second. We're just gonna talk about the angle and the radius. But this particular car is traveling along this track here. It's in circular motion. Most definitely, it's in circular motion. Let's have a look at the forces on this car. We know we have a force due to gravity, acting downward. We know we have a normal force that's perpendicular. It's perpendicular to the track itself. And because it's in circular motion, we expect to also be a centripetal force that's acting towards the center of this circle's motion. Now I want to, actually, a quick aside, I want to just be very clear here that this is not the same as this case here, where you have an object sitting on a slope and it slides down the slope. That is not what's happening here. This object is not sliding up or down the slope. It is maintaining the same height, so to speak, along the curve. Okay, so it's not this example here where you have a force down a slope and you've been accustomed to some of these equations. It's not the same here. Okay, so this is for a completely different scenario. Right, so if you're thinking, okay, I've seen this before, you've seen sort of something similar before, but they're not quite the same. They're not quite the same. Okay, so I'm just going to take this little bunch of arrows and triangles here and just make it a bit clearer. I'm going to draw it on the right. I'll use black. Here we go. Here we go. Okay, so here's my road, tilted very steeply, but it's okay. Very steeply, and here's my car. I'll put it up here. Okay. Okay. Now, I'll use green. So it has a force due to gravity. Acting downwards. It has a normal force. Oops, let me draw that again and attempt to draw it a bit straighter. It has a normal force, sorry, that's perpendicular to the surface. That's a bit better. And notice how this normal force is perpendicular to the surface, so it's actually on a kind of diagonal. Now I can express this normal force as a horizontal component. I'll call this FNH for the component of the normal force in the horizontal direction. Oops, and it's also got a vertical component. That acts in this direction. Okay, I'm going to call that FNV for the normal force in the vertical direction. And now these vectors unfortunately aren't to scale because I'm not Picasso, but let's just have a look at the forces in play here. If this car is not going up or down the slope, okay, it's not going up and down the slope, or it's not accelerating up or down the slope, we can assume then that this force here, the normal force in the vertical direction and the gravitational force are equal. That means it's not accelerating up or down the slope. So I want to connect the normal force in the vertical direction and the gravitational force together. I'm just trying to see how the forces work with each other. Now before I do that, I just want to make a quick little mention that let me just quickly sketch it in here in black. Okay, so if this is angle theta, then I know that this here must also be angle theta. Okay, we can see you've got kind of a Z going on. We've got two parallel lines and a transversal in between, so this angle here must be co-interior with this angle here, so they must be the same. So this is your angle theta, and let's call this angle here x. We know x plus theta must equal to 90 degrees because this here is 90 degrees and these other two must equal to 90, so the triangle equals to 180. So this here equals to x. Okay, and then this here equals to theta. The reason why this here is x is because the normal force is perpendicular to the surface. So we know that if this is theta, then this must be x, because it's the only angle which, when added to theta, can actually get you to 90 degrees. And then I applied the same kind of thought process to recognize that this angle here is theta. Okay. So let's continue. So now I know. Let me get rid of x for a second. We know where theta is. Let me just get rid of that. I'm just going to only focus on the things we actually need. Okay. So I want to connect the normal force to the gravitational force. So I know that FNV, the normal force in the vertical direction, FNV, okay, is, well, this is the adjacent side of the triangle. This is the hypotenuse. This equals to the normal force, the just full magnitude of normal force, cosine theta. And you can prove to yourself this is adjacent, this is hypotenuse. Okay, and you can do the relevant trig problems, that this here must be equal to Fg. Okay, so I know that Fn cosine theta equals to Fg. Alright, wonderful. Well, that's nice, I suppose. That's nice, I suppose. Let me just put that in red, perhaps, just to highlight its importance. Okay. But what about this horizontal component? What is it equal to? Well, it doesn't really have anything else in this direction. It doesn't have this. Okay, and we're ignoring friction in this case. We're assuming that that we don't have friction on our side, so we're just relying on this banked track to keep things in motion. What is this actually equal to? Well, notice that this component here, this horizontal force here, is acting towards the center of the circle. Now look at this diagram. The centripetal force was the force acting to the center of the circle. So really, the centripetal force is the normal force acting in the horizontal direction. So I can write that Fnh, which equals to Fn sine theta. Alright, here's your triangle. This is the opposite side. There's your hypotenuse. So the normal force in the horizontal direction, which equals to Fn sine theta, must equal to Fc. Okay, I'm just going to write that again down here. The normal force, the full magnitude of the normal force, multiplied by sine of the angle of the track, equals to the centripetal force. Again, I'm going to just make that look a little more important. Okay, in essence, what's actually happening here? We don't have friction on our side, so what's happening is that we are using the normal force to help us in our circular motion. So what are we doing? As opposed to having just an object sitting flat on a piece of ground with a normal force sticking straight up, we have a normal force here, which is at an angle. So it has a component of that force, which is in the direction of the centripetal force, or where we want a centripetal force to act. So we are using the the normal force which is acting on an angle to give us a centripetal force and allow that object to travel in circular motion. Okay? So that is the benefit of a banked track. By tilting the normal force, hence having a component of the normal force providing providing a centripetal force because it acts towards the center of the circle. Now have a look at these two formulas here that I've drawn in. Have a look at those. We can actually connect them together. So I can write that Fn sine theta equals to Fc. And what I'm going to do is I'm going to take that's the lower equation down here. I'm going to divide that by the top equation. So I'm going to divide that by Fn cosine theta, which it equals to Fg. So I've just taken one equation and divided by the other equation. Okay? Now, these two cancel out. They just become 1. And sine theta divided by cosine theta is tan theta. So I know that tan theta equals to Fc over Fg. Okay? If you wanted, you can actually simplify further, and you can see what comes out of this. Tan theta equals to, well, Fc is mv squared on r, beg your pardon, divided by mg. Okay? So you're going to get your m's cancelling out, you're going to get a g in your denominator, and so therefore tan theta equals to v squared on gr. I've written a 3 there because I can't write with a mouse. V squared, there we go, and hence v squared equals to gr tan theta. Okay, now let's just have a look at these equations for a minute here. Okay, so we've connected the normal force to the force due to gravity, and we've connected the normal force to the centripetal force. We can connect them together via this equation here. The tangent of the angle of the track equals to the centripetal force divided by the force due to gravity. Okay, now if you expand out Fc and Fg, you can write this equation here. V squared equals to gr tan theta. Now, this here is known as the optimal or quote-unquote design speed of the track. So you might see it both written as either design speed or optimal speed. Okay, and this is the speed at which you don't actually need frictional forces here to help you stay on the track. In reality, there are frictional forces in play, and they make the situation a bit more interesting. But at this speed and on this track, if you're traveling at exactly this magnitude of velocity here, according to this equation, then you don't need a frictional force to help you maintain your path on this track. Okay, so that is the optimal speed. Now notice that if you're maintaining the angle of the track, g can't change unless you go on a different planet. If you start slowing down, what is actually going to happen to the path of this car? Now, don't even look at the equation here. We expect that if you slow down, then maybe your car will end up traveling on this path here. Right? It'll start falling inwards towards the center. Okay? What if you're traveling too fast? Well, if you're traveling too fast, you might expect, you're going to end up sliding outward and traveling up here. Whoops, didn't mean to draw that. But anyways, there it is. Okay. Well, that's what we expect. Does the maths actually replicate that? Well, let's have a look-see. I'm just going to rewrite this equation here a bit more suggestively. V squared over g tan theta equals to r. Okay. If v goes down, if I drop my speed, then and these remain constant, then r must also drop as well. And so we do see that if our velocity drops, then the radius of our turn must also drop as well. And conversely, if our velocity went up, then our radius of our turn must also increase, and hence our car would slip up the banked track, trying to achieve a greater radius. Okay, and unfortunately, if this track isn't infinite, you're going to end up just sliding off the edge of the track. Okay, so in essence, these 1, 2, 3, 4 equations are the things you need to know. Now, really, you only need this one and this one to directly connect velocity to force, to the acceleration due to gravity, the radius, and the angle. But if a question asks you to directly link the normal forces, you can refer to one of these two. Okay? And there you have it. There is the theory behind banked tracks and why it is useful for making turns.